Hello guys, today I'll be reviewing topic C.3 in the IB Physics HL syllabus. Topic C.3 is named Wave Phenomena, and it basically talks about two things. The first thing is actually very small, I'll get through it quickly, which is Snell's law. So let's start. Snell's law states that the angle of, or let me explain first, write down the law and I'll tell you what it means. So, what is this? Let's start with the N. If you know, I think you've at least encountered what refraction means once in your life, of course, before even IB. It's very simple. It states that when light, in this case, moves from one medium to another, it refracts. This movement between mediums is called refraction. So, what does N mean here? N is the refractive index. It is basically the speed of light in a medium relative to the speed of light in a vacuum. So the speed in light in a vacuum, C, normally is 3 times 10 to the 8. So this happens when n equals 1. So to get any n value, you just see the speed of light in that medium. So for example, if the speed of light is v equals 6, or let's say 10 to the 8, well, it is simply 3 times 10 to the 8 divided by 10 to the 8, and that would equal 3. So that median's refractive index is 3. So this law states that the ratio of refractive indices equals to uh, the angle of refraction, which is theta 2, divided by the angle of well, sorry, the angle of refraction divided by the angle of refraction in the other medium. Or sorry, no, it is the angle of refraction, which is theta 2, divided by the angle of incidence. So let's see here. I'll draw it out for you. So light strikes uh, and goes from air, where we also assume n equals 1. So this is air, n equals 1. So V equals C at an angle theta. Since it's in the maximum speed, it goes into, let's say, water, and now it refracts. So it bends uh, towards the horizontal more and uh, away from the vertical. And you always measure the angle to this vertical, so it's theta. And this is theta 2 with the angle of refraction, and this is theta 1, the angle of incidence. This is n2, which is, we don't know what it is, and this is v2 because speed will change. So another important thing to know, that speed must change, because when you go from one medium to another, the frequency is always constant no matter what. But the wavelength of the wave actually decreases. They become closer together. So if they were like this before they refract, they will become like this after they refract. So if wavelength decreases for a constant frequency, then velocity must decrease. So now we've got that out of the way, let's get to a more important topic, which is diffraction. So what is diffraction? Well, diffraction is simply when a wave passes through a slit which is smaller than its wavelength. So for example, here we see these waves are larger, so when they pass through the slit, they bend. So they become like this. Okay? Uh, Diffraction, something you do not know about diffraction, is that when you diffract light specifically, it creates a a pattern, let's say. It creates a diffraction pattern, which I'll talk to you about. So, this experiment is known as Young's double slit experiment. What he did is simply get a laser beam and pointed it at two small slits. So this is, let's say, slit one, and this is slit two, of equal width. And since light is wavelength greater than the slits, it diffracts. And he set a screen here. Let's say it was d meters away. Okay. So he observed something. What did he observe? For light, he observed that it created a pattern of bright and dark fringes. So some places had light, while other places were completely dark. And that pattern continued and continued throughout the screen. He also realized something, that at the center, so distance d from here, about here, light was brightest at here. And light was the widest, and this is known as the central maxima, where light is widest, so it creates a wide light. So we like this, for example, and it is the brightest here, most intense. This pattern continues. So if you want to show it like this, we can to the right and left, where these points are minimas, no light, and these points are maximas, where there is light. And that continued forever. Okay? And this equation describes that experiment. It states that the distance S is the distance between two adjacent maxima or minima. So we state that these two are maximums, correct? So this is distance S. And even you can do it between minimas too. These twos are minimas, so this distance is also S. Okay? Lambda, of course, is the wavelength of light. D is the distance between the slits and the screen divided by D. So what is D? Well, D in double slit experiment is the distance between two slits. So D here would be this small part. And now you rearrange. If given 3, you can get the fourth variable. So we know that the distance between two adjacent maxima or minima is equal to lambda D over D. Okay? Now I'm gonna move on to the HL part, which is single slit interference. So single slit is similar to double slit, but now this is the slit, same laser beam pointed, and you have a screen is observed, or a pattern. So what pattern is observed here? Well, it is quite similar. First, what's similar here is there is a high central maxima. Central maxima here, let's say, with the highest intensity. But the difference here is here the maximas are always at the same intensity. Intensity doesn't increase. But here, maximas, the intensities start to decrease. So becomes this, then becomes smaller, then becomes smaller until they hit zero. And here is the same case to both sides. So this is the only difference between two slits, double and single slit. And the equation to find the distance between two adjacent axina is actually not a distance. It is given in radians and an angle, and from that angle you are able to get the distance using trigonometry. But in our syllabus, we only need to get the angle, which is called the angular distance. So it's simply theta, the angle, equals lambda, the wavelength, over b. B is simply this, the width of the slit. Okay, so now that I've Explained. Let's start solving some questions. In a double slit interference pattern, which change would cause the fringes to move closer together? So let's write down the equation. S equals lambda D over D. So the distance between slits would be S. So what would cause S to decrease? A. Increase the screen distance. While increasing this would also increase this. So A is incorrect. B. Use light of shorter wavelength. While decreasing lambda would also decrease S at a constant of the others. So it is B. Okay, a wave travels through a narrow gap and spreads out. Which factor increases the amount of diffraction? Okay, let's see. Making the gap wider than the wavelength. Well, if you make the gap wider than the wavelength, no diffraction will be observed as light will just pass through. So A is incorrect. Increasing the wave's frequency. Well, wave frequency has nothing to do with diffraction, so no. Using shorter wavelength. Well, that would also be incorrect, since using shorter wavelength would make diffraction less, since there is more, the wavelength may even be smaller than the width of the gap, or it would be smaller, so minimal diffraction would be observed. D would be the right answer, but let's see what it says. Using wavelength similar to the gap size, which is correct. You need to use a wavelength of similar gap to the size in order for diffraction to be observed. Okay, this is about Snell's law. So a wave travels from medium 1 with speed 300 meters per second. So V1 equals 300 to medium 2, where V2 equals 500. In material science experiment, the wave strikes the boundary at an angle 30 degrees. So this angle he's telling us is the angle of incidence, which we call theta 1. So theta 1 equals 30 degrees. Well, we're given three givens using Snell's law that states that V2 over V1 equals sine theta 2, which is the angle of refraction, divided by sine theta 1. So simply V2 over V1 would be 500 over 300 equals sine theta 2, which we do not know, divided by sine 30. So rearranging this would give us theta 2 equals 500, or let's say arc sine, which is the inverse of sine, arc sine 500 sine 30 divided by 300, which equals. So make sure to give your answers in degrees, since they give you the angle of incidence in degrees. So arc sine, and you'll have your calculators in both papers, so do not worry. Sine 30 divided by 300 will equal 56.4 degrees. And let's see if the answer is correct. It is correct. Okay. Sketch the wavefronts as they transition between the two media. Well, the first thing you have to know is that the speed has increased, meaning that medium number 2 has N2, which is the refractive index of the second medium, is less than that of N1 because the speed is greater. So let's say wavefronts are moving from the first medium and they strike at an angle here. So they move, since this is a less medium or less refractive medium, so they become straighter or move closer to the vertical, and the distance between the waves increases. So the wavelength increases since the speed increases. And now you've got your sketch. Okay, this is very nice. Which unit is used to express the number of lines on a diffraction grating? Well, simply lines per millimeter. Hmm. Okay, which factor affects fringe spacing in a double slit interference pattern? Well, again, you write down the equation or look at it in your data booklet. So A says the width of the slits. Well, actually, this equation does not include the width because in double slit, the width does not matter. The width only has to be, only thing that matters about the width is it's small enough for diffraction to occur. It cannot be wider than um, the actual wavelength of the beam. So B, the thickness of the screen, incorrect. It has nothing to do with diffraction. C, separation between the slits. Yes, separation between the slits is D, small d here. So it is inversely proportional to S, so it does affect it. Okay. What changes occur to frequency and wavelength of monochromatic light when it travels from glass to air? So as soon as you see frequency here, you know that frequency never changes in refraction. So it will stay the same. So now we have C and D that say that frequency increases or decreases, so you can keep them away. And we know when light travels from glass, which has higher refractive index than air, because air is the least, if and in IB curriculum, we assume it's like a vacuum, so n equals 1. So we know that the wavelength will increase because the speed will increase and frequency stays the same, so the wavelength must increase. So we have here B, which says that the frequency stays the same and wavelength increases. Okay, let's see. A monochromatic light of wavelength lambda is incident on a double slit. One slit is filled with a transparent material that shifts the phase of the light by pi. The distance between the slits is d and the distance to the screen is d. What is the distance from the center of the interference pattern to the first maximum, and is the central fringe a dark fringe or a bright fringe? Well, it says a phase shift of pi, so it's definitely dark because I don't know how to tell you this, so let me. Well, no, actually, a phase shift of pi means it stays. It actually stays as the same. If you write, for example, a sine wave, here is 0, and here is pi, and 0 pi are exactly the same. They're both zeros. So no, phase shift of pi over 2 would actually make it different. So it is a bright fringe. And the equation would stay the same, which is lambda d over d. So the answer, oh sorry, the actual, yes, the answer is what I just said. In a single slit experiment, what happens to the central maximum if the slit width is decreased? Well, theta equals lambda over b. So if you decrease b, you increase theta. And theta is the angular distance. So actually, another thing I forgot to tell you is that the width of the central maximum is equal to the distance between any two maximas or minimas. So if you decrease b, you increase the width of central maximum, it becomes wider. So what type of interference occurs at a point where two waves meet in phase? So meeting in phase means constructive interference. You have to know that. So maximas meet with maximas and minimas meet with minimas. Maxima will never meet with a minima, or a minima will never meet with a maxima if they are in phase. If they're out of phase or a phase of pi, That's when the destructive interference will occur. And I want to tell you something else. In order for diffraction pattern to be observed, we have a term called coherency. Two waves must be coherent in order for destructive or constructive interference to occur. So what does coherency mean? Well, coherency means that the waves must have two properties. They must be in phase and they must have the same frequency. Okay, a single slit diffraction pattern is observed with a slit width of A. So let's write down the equation, and since he said the slit width is A, we can substitute it for B. So theta equals lambda over A for this question. When the slit width is halved, the angle to the first minimum, well, this is halved, this is doubled, so B. Okay, now let's write the curriculum. I'm trying to find the question. Okay, which of the following would result in more diffraction in a single slit interference? So more diffraction means that theta increases, the angular width would increase. So let's see, using a wider slit, well, that's incorrect because theta would decrease. Using a higher frequency of light, frequency has nothing to do with diffraction. So using a slit width similar to the wavelength, well, that would actually work, or increasing the distance with the screen, which has nothing to do, which would be actually be using a slit width similar to wavelength. Okay, which wave phenomena explains why light bends around small obstacles? Reflection, refraction, diffraction, or polarization? Well, the answer would be diffraction, of course. Okay, which of the following best describes the cause of dark fringes in an interference pattern? Light is absorbed by the slits. Well, that's of course incorrect. Two waves arrive exactly in phase. Well, if two waves arrive exactly in phase, they will constructively interfere. Two waves arrive exactly out of phase, which is correct. What causes the central bright fringe in a single diffraction pattern? All rays cancel at the center due to destructive interference. All rays arrive in phase at the center, which is the correct answer, something you need to know. So let's solve the final question of the video today. Okay, two coherent sound waves emit wavelength 0.5 meters at a point, so 0.5, at a point 2.75 meters from one source and 3 meters from another. So D1 equals 2.75. So as soon as you see this, there's a difference 0.25 between them, okay? And what does 0.25 mean? That means that there is a phase difference of half lambda, because that is half the wavelength. So when the phase difference is lambda over 2, it automatically means that destructive interference will occur, and that is one of the answers here. If the phase difference, I'll tell you something very easy. If the phase difference is, or path difference, path diff equals k pi, where k is an integer, this means constructive. And it is the same actually for phase difference if it's given. But if path difference equals k, also an integer, pi over 2, it is destructive. And of course, at 0, it is constructive, if you cannot tell, because if you let k equal 0. Let's solve the final question. Okay, in a double slit interference pattern, bright fringes are observed on the screen. What causes these bright fringes? Polarization of light at each slit? No. Destructive interference of light? Well, that would cause dark fringes. Constructive interference of light, which is the right answer. So, today we reviewed topic C.3. We are almost done with topic C in the IB Physics HL syllabus. We talked about Snell's law, refraction, and constructive and destructive interference in both single and double slit experiments. So, thank you.